Okay, hello everyone to today's seminar on interval methods in control engineering. And it's my very great pleasure to welcome today Thach Dinh from the Conservatoire National des Arts et Métiers à Paris. And Thach will talk today about fixed time interval observer design using an artificial delay. And especially he will deal with a case study on discrete time systems. Thach, the floor is yours.
Okay, thank you, Andrea, for inviting me to give a talk today and for the introduction. So my talk is maybe a little bit different with respect to most of talks in the frame of this seminar, because here we do not consider any algorithm or any LMI or something. The technique is rather analytical and based on mathematics. So the title of my talk is about fixed time interval observer design using an artificial delay, and I will study two family of discrete time systems. I'm from Conservatoire National des Arts et Métiers, like Andrea have presented. Now, here is the outline of my talk today. I will start with an introduction, and two main parts of my talk is about I will review the time invariant discrete time systems and time varying discrete time systems. And next, a small application to switch linear discrete time systems. And finally, I give a conclusion and some future work. So now we go to introduction. First, I would like to share some remarks related to the talk. In applied mathematics, using time may have to overcome obstacles. An example, for example, if you are familiar with interval observer design, so the chain of coordinates normally in time varying, even if the system is time invariant. So here in the frame of this talk, I will use an artificial delay. Here artificial, I mean I will intentionally insert a delay in the observer design of a system without the system having to depend on the delay or to rely on past inputs or states. And I will review two families of systems where using an artificial delay can be useful for first time observer design. I will make clear the context and the goal of my research. So the context here quite different from normally. Here I suppose that we have no appropriate knowledge of the initial conditions, and we have no monotonicity property. For classical design of interval observer, those assumptions are a must, or even when we use some Jonathan or ellipsoid technique, we still need the bounds of the initial condition. So the goal here, so as you can see in the picture here, the system may be affected by disturbance and the measurement may be affected by noise. In the case if those uncertainties are known, or we can say that if there are no uncertainties, we will give the observer will give an exact estimate after a fixed time S. So in the frame of this talk, the fixed time will be noted by S. And in the case, of course, these assumptions are not realistic because most of the time we have to cope with disturbance and noise. And in the case where we have to cope with disturbances and noise, our technique will give an interval estimate for on time k greater than the first time s. So let me recall you about classical observers. For classical observer, we can reach the goal of only asymptotic estimate and not an exact estimate when k tend to infinity. Normally we cannot play on the conversion time for classical design. So here we have some advantage. So we give exact estimate and we can tune the conversion time. For interval observer, if I recall you for interval observer, we will design two bounds for on k, but we need two assumptions, two very important assumptions about the non-bound of initial condition and some monotonicity or non-negativity properties. And in this talk, we do not consider those assumptions. So this the second advantage. So there are two advantages. We can give exact estimate when we have no noise and disturbance, or we call it deadbeat estimate, and we will give an interval estimate without knowing the bounds of initial condition and without considering the monotonicity properties. So what are deadbeat estimate and what are fixed time interval estimate? So exact estimation, that means we will reach the exact estimation as you can see on the left hand side, the figure on the left hand side. After fixed time S, which can be tuned, we can reach the exact state of the system. In case the absence of disturbances. And the first time interval estimate, that means after first time S, we will build an upper bound and a lower bound as usual for the real state of the system after first time and in the presence of disturbances. Of course, we need the bounds on disturbances and noise, but those assumptions are realistic in most of the case in application. So what is the key idea here? So the key idea here, we will use the path value of the input and the output of the study system to build the deadbeat estimate. And if once we already build the deadbeat estimates, the construction of interval estimate is quite simple because we just need to add the frame of the disturbances and noises, so we can obtain the interval without difficulty. So the challenging here is how to construct the deadbeat estimate. So the idea is based on one paper in 22, and I really recommend you to read this paper. It's a very short but an excellent paper, giving a very interesting idea. Let me recall you about the advantage of the proposed interval techniques. So compared to classical designs, we need either monotonicity property or information on the bounds of the initial condition, or both of them. even if we use some zoonotopic method, we still need the information on the bound of the initial conditions. And our proposed technique can help in avoid those assumptions, and moreover, it can give a fixed time and interval estimate or a dash bit estimate. Now we go to the first main part of my talk today. I will review here the time invariant discrete time systems. So this work has been published in the proceeding of a conference in 2019. Some notation and lemmas would help you to follow more easier my talk. The operators greater than or less than must be understood components wise. So here we understand what means components wise. So I do not need to explain. We suppose that for all matrix Q, square matrix Q, Q plus, as usual, that is the max of Q0, and Q minus Q plus minus Q. The value up the absolute value of Q equal to Q plus plus Q minus. So those relations are famous in the frame of interval design. And the famous inequality. So if a vector D are bounded by known vector, and if we have a constant matrix M, so we have those inequalities. The proof is very simple. Here is the key relation of the key idea of my research or my talk today. If we have a nonlinear discrete-time systems with disturbances, that means xk plus 1 equals to axk plus fuk yk plus dk. We can always relate the state at time m1 to the state at an earlier time m2 as follows. For time invariant systems, we can compute easily the state transition matrix. That's a power m1 minus m2. Of course, this relation is very simple to prove. And here is the considered systems. So for considered systems, I will note it at S as a considered system with the output yk affected by measurement noise. We suppose two realistic assumptions, that means the disturbance and the measurement noise are unknown but bounded by known values. And the second assumption is also classical in observer design, that the pair AC is observable, and the matrix E is invertible. That's this one is the new assumption in our design. We require that the matrix A should be invertible. AC observable, that means that there is always a matrix L such that the matrix S equal to A plus LC admits a spectral radius smaller than the modulus of any eigenvalue of A. So we can prove that there always exists an integer S such that the matrix S power minus S minus A power minus S is invertible. The proof is given in the paper. It's not complicated to prove that there exists always a fixed time S to satisfy the invertible condition of this matrix. And so we can define the invertible matrix as ES is the invertible matrix of S power minus S minus A power minus S. So if A is not invertible, we can always find a way. We can always find a way to decompose AX plus FUY in an alternative way, so that the new matrix A is invertible. So that this assumption is not really a challenge. So now we will go to more detail of the proof, the computation. So we because S equal to A plus LC, and we have output Y. So we have two equivalent representations of the considered system S. That means that's one. The first one is the considered system, and the second one we replace A by S minus LC. So we can obtain the second representation. So now we will use the pass value of the input and the output. But first, let me recall you about the relation I introduced in the last in the previous section. Now we just need to apply for M1, we will replace it by K, and M2 we replace it by K minus S. So of course K is greater than K minus S because S is a positive delay. So we can have the following two following equations: xk in function of A and xk in function of S. If we apply this relation in the two above mentioned equation systems. Now we just need to take because the matrix A and S here are all invertible, so we just need to multiply both sides by A minus S and S power minus S. We obtain the two next relation. Very simple. We just need to multiply both sides by the invertible matrices of A and S power S. And now please remark the color code. The purple one, the blue one, and the black one. So if we take the second relation minus the first relation, we can obtain the following relation. That means the black terms equal to the purple one minus the blue one. And now you see that we can compute the state xk because this matrix is invertible. We have chosen S such that this one is invertible. So if we would like to compute xk, we just need to multiply both sides by ES, and we can obtain the exact value of the state xk. And this one is the first theorem. We just suppose that we have S such that the matrix S power minus S minus A power minus S is invertible. Then we can always compute the state xk by multiplying both sides by ES. With ES here is defined as follows: is the invertible matrix of A S power minus S minus A power minus S. So what is the drawback here? So of course, as you can mention the drawback here, the formula may contain many terms because S may be larger. We can choose a S. So if we choose a S very large, many values have to be stored. So that's give a motivation to find an alternative solution would be based on dynamic extensions. And we have the theorem 2. For the theorem 2, we will use two dynamic extension. The second one, the X star is, if you mention, is a classical observer for the system, the considered system, when disturbances are known. And we can do the same process to apply the well-known relation in those two dynamics. So we can replace the bubble terms and the blue terms by some dynamics, and we can compute the real state of the system for on k, of course, for on k greater than s. So is the exact estimate. Once we already designed the exact estimate, so what we need to do is to design an upper bound and a lower bound for the real state of the system in case the system is affected by disturbance and measurement noise. Idea is very simple. So we will first design an exact estimate for the considered system without disturbances and noise. We have two parts. We can decompose the exact estimate into two parts. The purple part is the part without uncertainties, and the second part regroup. The second part contains all uncertainties. And if we would like to bound the state or design an upper bound, we just need to keep the bubble term, the bubble terms here, and we replace the term with uncertainties by the upper bound of the uncertainties by using the famous inequalities in interval observer design. Okay, so we can have the upper bound. Similarly, for the lower bound, we keep the bubble term and we just replace the uncertainties by the lower bound, by each lower bound, and we can obtain the lower bound of the real state. And equivalently to theorem 2, we have theorem 4. We use some dynamic extensions to simplify a little bit the representation of the design. We just replace some terms by dynamic extension, and we can obtain the upper bound for the state. If you remark, the bubble term here the exact estimate, the exact estimate without uncertainties, and the blue part are the upper bound of the uncertainties. And similarly, to compute the lower bound, we keep the bubble terms and replace the uncertainty by its lower bounds. So that's the idea of using an active cell delay to design an exact estimate and an interval estimate for time invariant discrete time systems. We come finally the end of this part. to consider a numerical example, and we can choose a matrix L giving S equal to A plus LC invertible and shortable. We can easily prove that for this example. We can easily prove that S power minus S minus A power minus S is invertible for all S greater than 2. So all assumptions are satisfied. So we can plot the exact estimate as you see on the picture. Here I try some value of S. The first one is that S equal to 2. You can see that we obtain the exact estimate after 2. And second one I try with 5, and similarly we obtain the good simulation of the theoretical result. For interval estimate, if we consider some disturbances and measurement noise, in this case we can obtain 2 bound of the real state after a fixed time, which can be selected. Here I select 3 and 4. So as you can mention, I choose 2, 3, 4, 5 all kinds of the fixed time, and many different values of the fixed time, and the result of simulations are good and can illustrate the theoretical development. It's the first part of the talk. So now the second part, we will generalize the first part for time varying discrete time systems. So this work has been also published in one paper in the proceeding of ACC 2020. The challenge here is about the state transition matrix. Now it's not we cannot have the analytical form of the state transition matrix. It's generally is a matrix phi, and we can always relate the state at time m1 to the state at an earlier time m2, where the state transition matrix is computed as follows: is equal to A at time m1 minus 1 multiplies A at time m1 minus 2 until m2 for all m1 greater than m2 greater than 0. And if m1 equals to m2, it is an identity matrix. We can remark that if all matrix, if matrix A is invertible at all instant from m1 minus 1 to m2, so the matrix phi here is also non-singular, and there exists invertible matrix of phi A that we note phi A minus 1 m2 m1, and phi A minus 1 the m2 m1 is exactly phi A m1 m2. And this relation is quite famous and has no difficulty to prove. Phi A from m1 to L multiply phi A from L to m2 equal to phi A from m1 to m2. So those relations are key idea for the development of this pattern. So now the problem statement, we consider the system SK, because here the considered system depending on time. And we suppose the same assumption on the observability and the bounds of uncertainties. We suppose that there exists matrix Lk until Lk minus S and an integer S star, such that for all S greater than S star, the matrix similarly the matrix phi S minus 1 minus phi A minus 1 is invertible. And we can define the invertible matrix of this one as the matrix ES as usual. So the same remark, if AK is not invertible, we can find an alternative way to decompose AKX plus beta k UK YK so that the new matrix AK invertible. The key idea is quite similar, so I will go it quickly. We just replace the A power M1 minus M2 by the more general form phi A M1 M2. And we can use that, and we apply that for the two representation of SK, and we can have two following relation. And because phi A is invertible and phi S is invertible, so we can multiply both sides by phi A minus 1 and phi S minus 1. And we recall that phi A minus 1 k minus S is equal to phi A k minus S k. So if we multiply both sides by phi A k minus S k, we can obtain here the matrix phi S, the k minus S, we multiply both sides by the invertible matrix of phi A and phi B and phi S. We obtain the following relation, and similarly we can compute the state xk by multiplying both sides of this relation by ES, and we have the next theorem, and the same drawback, and we replace some terms by two dynamic extensions, so we can compute the exact value of the state in the time varying case. Of course, if the system do not depend on time, we can replace phi S by S power k minus S. So we notice that X star is a classical observer for the discrete time varying systems. Similarly, we just need to keep the exact estimate without uncertainty, and we add the upper bound and the lower bound of the uncertainty part. We can obtain upper bound and lower bound for the real state of the system by using D-Fermat inequality. And we have the dynamic extension of the interval observer design as follows. Very similar to the first part. We just need here to change the state transition matrix by a more general form, and we can reach the objective of designing two bounds for the real state of the system. Finally, I will give you an example. This example is borrowed from the paper of Ngoc and An in 2010. And those one are discrete time varying systems. And we can plot three components of the state as follow. Here I choose some value of of the first time 3 and 4, and we can obtain the exact estimate or the interval estimate after a first time which can be selected. So the final part of my talk, I will give very quickly a simple application to suit the linear discrete time system. Here I have to mention that the switching property here are not a challenge, because we suppose that the difference between two switching time is always greater than minimal dwell time tau A, and greater than the first time S we choose. So that means we can reach the exact estimate before the next switching. So that means switching here is always is also a motivation. It does not affect a lot the design. I think that I believe that we can do it better, but I still do not have time to formulate the problem. So that's why I call it it's just a small application. And if we suppose that there exists a first time S to satisfy the minimal dwell time condition, and such that it Métiers is invertible, so we can plot the exact estimate of the state of the linear systems. So here the switching instant are known, so we can reset at its switching instant, and we do the same thing for employ from the first part of the talk, and we can obtain the exact estimate for the switch linear system. And similarly, for interval estimate, we just need to add the bounds of uncertainties, and we can obtain two bounds for the real state of the system after a first time. Here we choose the first time equal to 4, and here the first time equal to 2 and 3. Several different value of the first time, and this one is the switching signal. We choose the interval between two switching instant is larger than the first time. So let me conclude my talk today, and the key idea relies on the use of pass value of the input and the output of the study system. It's an artificial delay, because as you see, the system is not affected by delay, but the delay is added intentionally to the design to obtain exact estimate of the state. Neither information on the bound of the initial condition nor monotonicity property is needed in our development. We can provide exact values of the solution in the absence of disturbances, and a lower and upper bounds when the disturbances are present present after time which can be tuned. For future work, actually I do not have time, but I still I'm writing a work on extension to more general family of linear discrete time systems, because now we can add some noise into the nonlinear part of the system, and we can add as well some unknown inputs. Also, I'm writing one paper on this direction. And the last one, I suppose that we can use this observer to construct a feedback, which can be also expected. So thank you for your attention. and I'm ready if you have some question or comment.
Okay, then many thanks, Thach, for your very interesting presentation. And yes, I'm pretty sure that we will have questions. Is there anyone who wants to start? Okay, then let me start with the first one. Since you just mentioned extending your approach to nonlinear dynamic systems, where do you want to add the nonlinearity and in which way?
Okay, it's as you can see here. In fact, the system I consider is already a nonlinear system.
Yes, because you already have some nonlinearities with respect to the control input. You have also a nonlinear term with respect to the measurements.
To the measurement and the input, but not for the noise. So
okay.
suppose that we can add some noise in the nonlinear part here, because maybe the problem become more challenging. Actually, the disturbance is linear, so it's less complicated. So for a Juno version or something, maybe we can add some noise in the nonlinear part of the system, and we can consider also an unknown input. For now, we have some idea about some constant unknown input. That means the unknown input do not depend on time. I think it's easy to do, but if the unknown input is dependent on time, actually I do not have yet an idea to cope with this problem. The limitation is that for constant unknown input, maybe application is quite limited. But if you know some application, I will appreciate it for some simulation.
Yeah. There's one further point, I think, where nonlinearities are quite crucial is the first term, this A times the state vector. Because at the moment, you're just dealing with nonlinearity with respect to measured quantities, but nonlinearity with respect to non-measured state variables. I think this could also be something very interesting and challenging.
Very interesting, but the problem is that for this design, it become quite restrictive on this point, because if the nonlinear part depending on the unmeasured part, we cannot have this kind of thing. Because here, because here we can have this form, because the nonlinear part do not depend on the unmeasured state, but if it depends on the unmeasured state, it's quite restricted of this method to cope with that problem. I think.
Yes, I think that's one point where you could resolve this a little bit. In cases where you have nonlinearities that can be factorized.
Exactly.
Where you have some A of X multiplied with X, and then this A could be bounded in an interval matrix.
Yeah, maybe we can add some assumption to cope with it. Yeah, maybe.
Concerning this idea that I just mentioned, did you try out your approach also, or did you try to extend it to system models where your A itself is even a time invariant interval matrix?
Yeah.
Does this work easily? How would you propagate then the model? Is this then a sonotopic approach that you're using, or could you give any guidelines?
I still not think about it, but I will see. I will see when next month when I have more time, because actually I have a lot of teaching. I do not yet have time to look. It's for more general case, but I think it can open some interesting perspective for future works. I just need to formulate really a proper problem statement and see how I can do it.
Yes, I think there's especially one point that I liked very much in this presentation is your comparison between the exact estimate in the case that you do not have any disturbances and yes, the corresponding interval counterpart, and how you perform the comparison between both.
Mm-hmm.
Yes, and I think also this formulation, the nice thing, in fact, we can directly see it in the very last line here on this slide. The nice thing is it includes, for example, also things like a moving horizon, smoothing of signals. For example, when you have discrete time integrator models like xk plus 1 equals xk plus some unknown term, which would be your function beta here in this case. Yes, and this is moving horizon estimation. This is quite easily included here. And that's really
okay.
that's really nice, this formulation.
Yeah, thank you. Yeah, thank you for this comment. Yeah, and I have one more. If here the problem is that the computation is analytical, so it's very complicated to optimize the bounds. You know, we just add the upper bound and lower bound of uncertainty part, and we cannot have an algorithm to optimize those bounds. So it's also an issue of this technique. So supposedly, if the known bounds we know are too large, maybe it's an issue of the method.
Okay, then you have stolen my last question. Because my question is, did you already play around or have some heuristics that you can use how to optimize L in order to enhance your bounds?
If not for this method, but we use we can similarly method that's based on parity space method. We already consider it with Genhua in one paper to help us to optimize those bounds, and it has been published in Automatica last year, I think. It's not exactly, but it's quite similar. It's quite similar to we use parity space to do it and add some L1 optimization to help optimize those bounds, but not for this technique, not exactly for this technique.
Okay, then let's see. Is there now anyone else who wants to ask a question? If not, thanks again, Thach, for your presentation, also for answering all the questions.
And my pleasure to give a talk in your seminar, and
yes, and
have nice days to all the participants.
Yes, that's the similar thing that I wanted to say to all of the audience. Have a nice Friday afternoon, evening, and weekend. Yes, and we'll meet each other on Friday in 2 weeks for the next edition of our seminar.
Okay, thanks a lot.